Alright, so we have seen yesterday about the basic flow of CMOS fabrication, and we've seen how we can actually use these mask layers. For instance, we have this typical fabrication process where we talk about using the mask, different mask, a set of masks for inverter circuit. So there are about six masks called as annual, polysilicon, N plus diffusion, P plus diffusion, contacts, and the metals that we have used for specifically in a certain area on the wafer, and that's how we are able to create a transistor layout. This is called as transistor layout for a circuit. So what is this layout for? This is the layout for a CMOS inverter circuit, and masks are specifying. You see, this is the mask for N well. It is specifying where the N well will be manufactured on the chip. This is a mask for the polysilicon, is specifying which place on the wafer this mask is going, so that finally I'll have the circuit for the CMOS inverter. This is the mask for the P diffusion. I have this N diffusion, so this is the mask telling me this is the mask for N plus regions, N plus and N plus here, that is helping me to fabricate my NMOS, and extra one mask here that is helping me to tell this mask will be inside the N well to have a contact for the PMOS transistor, because PMOS goes inside the N well. Similarly, I have a P diffusion mask. So you see this colors, I have this mask here is showing that mask is to tell me where I want to fabricate my PMOS transistor, and you see this mask also, this is sitting inside the N well. Then this extra P diffusion region is to have the substrate contact, because I know NMOS is fabricated in the P type substrate. Then I have the contacts. What are the contacts needed? I have fabricated diffusions, see, N plus, and this is a P plus. Now this is P plus, and this is N plus. But then after having those regions, I need to have a contact or connections with them through the metal. It's just like you build some circuit on the breadboard or on the PCB. Then you take some extra metal wires and you do the soldering to have their connection with the external world. So this is what the contact. And final mask is about the metal, right? So where I want the metal, because I know that this body of the NMOS and the source are connected together, and finally they are tied to ground. Similarly, the body of the PMOS, which is the N well, and the drain of it is connected together, and together they are going to VDD. This is how the inverter looks like. And in between this source of it or drain of it and this source of it or drain of it, they are tied together to form the output connection Y, and the poly are connected together to form the gate. So I had asked you if I have drawn this layout for the CMOS inverter. How about I give you an output function Y equals to A and B, and I have a bar over it. So it's a NAND logic, I know that, right? So I had asked you that come up with the top view. What I have shown you is the top view. This is the top view of the layout, and the cross section is easily also can be drawn as we had seen before. So have you come up with the top view, or in other words layout of this NAND logic? So NAND logic tells me that using the compound logic gates I can have the NAND structure. So what I see here, I have two transistors. These are NMOS transistors. So I have them connected like this, A and B, and in parallel what I have is the PMOS transistors. They are going in parallel, and that's the connection to the VDD, and this is a ground, right? So this is my NMOS 1, 2. So and there are the same inputs A and B, and I know here is somewhere my output. So inputs are A and B and output is Y. I know how this circuit works, and based on that I have the logic equation or the logic table for that. Now the assignment was to draw the layout for this circuitry, for this logic circuitry. So have you done that? I had asked each one of you to just come up with that idea. Use the different masks. How many masks we'll need? Total 6 masks. So how many of you have done that?
So I already sent it to you.
Okay, she has done. So let us just try here, just to briefly, before we go to next slides. I am wanting you to understand how we will approach this problem. So I know that this is an NMOS transistor having input gate, B input to the gate. Here is a input, and I draw the structure. I designate the symbol like drain and source. Then again, this is drain and source, or they can be interchanged also. Now this is source and drain, and this is source and drain, right? So assuming that I have a P substrate right here, this is my P substrate right here, but I'm not drawing the cross section, so I want to draw the top view of the layout. So I will use the different set of masks. What are the set of masks is that? So for instance, I know that just I will follow these slides here. You can see this slide. What I do here, look at this slide. So I'll draw this layout here, somewhere here, so that you can relate to that. So what I do is that I have two transistors here, NMOS right here, A and B. This is ground, and this is, then I have a PMOS about here, A, and then I have, this is another transistor B, and that's VDD, right? And then here is the output of this logic, and I want to draw the layout. So what I first do, just for my sake, I will define the terminals, drain and source. This is drain and source, this is source, drain, source and drain. And just for simplicity, I am not drawing the body connections to this. So what I do is that first I want to I can start with any transistor. So let's say I want to draw the N mask. So for instance, so here I am going to draw the N well. This is N well, and I know that here is going to be my two transistors. These are the contacts, okay, just like shown over here, and there is this polysilicon gate that is I am drawing here, just like here you see that I am not drawing the body of this PMOS here, okay. Similarly, I am seeing that there is another N well for which I will draw my transistor, because I need two transistors right here. So I see that I have drawn the layout for this PMOS again, okay. So this is PMOS number 1 and this is PMOS number 2, right? And then what I do here is that I have NMOS here, for instance, so I'll use that another right here. Let's say I use the another mask here, so this is, and there are the contacts. This is N plus heavily doped regions, and somewhere here I am using these two ones. So this is NMOS again, and this is NMOS again. So once we do that, how can I draw the connections? I need that, I know N well, okay. So inside that I need probably the mask. I have to use the different colors. So let's say I use, for P plus diffusion, I use this color. This is N wall and this is the diffusion, okay. So don't get confused. And that's the color, red color is for the N plus diffusion, okay. P plus diffusion is with the dark green, N well is with the light green, okay. And polysilicon gate maybe we draw with black colors. So just to identify and differentiate between these two, so don't get confused with that. So you have this polysilicon, and for metal and contacts we'll use another different color. So let's say for the metal I am going to use the yellow. So here is the yellow, right here. So all different mask has a different colors here. Okay, so how to make the connections? What I know here, first of all, metal, for metal which color you want to use. For instance, I am using let's say a blue color for the metal. So what I see, the source of this transistor that's connected to the ground, then I see the source and drain of these two transistors, they are tied together. So can I make the connection? Once I am done with this, it's very simple. So this is, let's say I say this is drain, this is source, is drain, this is source, or you can interchange it also. This is drain, this is source, this is drain, and this is source. So I see now the source, so I have to draw the metal now. So source is connected to the ground, so I will just say somewhere here it's the ground. I'm just drawing the wire, assuming that this is the mask for the metal. Okay, and the drain is connected to the source of this. So why don't, this is the source and this is the drain, so they are tied together. Okay, and what else? I see now that these two drains are tied together. Okay, so let's say I call it drain, here I call it source, and these drain are tied together. So I will just cover this right here.
Sir, is that poly or metal, sir?
I'm drawing the metal now. Poly is this one, these rectangles are poly, and now what I am drawing are the metal.
Sir, in the inverter, gate to gate is connected with poly, sir.
Yeah, but then you will have to connect the metal with the poly also.
No, like why gate to gate is connected with poly and source to source, drain to drain is connected with metal in the inverter.
Okay, right here, right? Okay.
Yeah.
Yeah, because the gate, we know that the structure that we say that it is NMOS. So it is semiconductor, this is silicon dioxide, and this is metal, right? This is the basic operation of the MOS transistor, right? We know that. So we on top, yeah. So this transistor is traditionally, this is how the transistor was fabricated when the MOS was invented, and I also explained you in few of the earlier sessions. So nowadays the technologies, because of some technological advantage, this metal is not deposited on the oxide, rather semiconductor called as polysilicon, crystalline polysilicon. It's just like a silicon, but they are calling it as polysilicon. And that semiconductor is just a silicon, but it is heavily doped, so it acts as a good conductor. So it's same as the metal, and it has some advantages because of the technology point of view. That's why they don't use the metal, rather they use polysilicon.
So polysilicon is act as nothing but a conductor, no, sir?
Yeah, because it is heavily doped.
It is not a semiconductor.
It is a semiconductor with heavy doping, so it is as good as conductor.
Okay, sir. And in the manufacture, always they will use poly to connect between gate to gate only.
Right.
For other connection, normal connection and all, they will use metal.
Yeah. The gates will always be formed with the polysilicon. Every transistor will have its gate made of polysilicon.
Okay, sir.
It may be possible that two gates are, let's say for instance you have A and B here, right? You have a polysilicon deposited here. It may be a choice of a designer based on some particular need or design need. There could be a metal connection connecting the two polys together.
Okay, sir.
Okay, so you see now these drains are connected and the sources are tied together. So source are tied together, so I will take these wires here, and that becomes my connection to VDD. This is VDD here, because sources and drains are tied together, so that becomes output Y. And where is the coming? The drain of this transistor is coming to the Y junction. So drain of this transistor So somewhere from here I will go like this. So it's just to show you the simplicity. This is how the connections will be made. So this is just a simple rectangle. So you see now, this is just you want to do the routing and wiring to draw the layout for this one. We'll learn this in more detail, but this is just to give you an overview about how things will be connected together. Here the source is connected to the ground. So what I'll do is that, if suppose this is the source now, so I will again draw the metal wire, and this became my ground. Okay, are you getting my point?
Yes, sir.
Yeah, so we move next now. So coming back to our fabrication process, yesterday we saw that how we fabricated the N well. So we started with bare P silicon substrate here, right? And then what is the first step? We perform series of steps. So series of steps in the sense, we first started with silicon dioxide. We grow the layer of the silicon dioxide on top of the substrate. Then we use this organic polymer called as photoresist. It's the special type of plastic or say organic polymer that is spun coated on top of the silicon wafer. Here it is spun coated on top of the SiO2. Then we decide which area of the silicon wafer we want to fabricate N well. So we chose that, okay, somewhere here I wanted the N well. So what I do is that I go back to this diagram. Now I am just deleting the ink here. So I go back the diagram and I see out of 6 masks which mask I will take. I know N well I need, so I will choose the mask for N well. So this is how the mask of N well looks like, and on this portion I am going to fabricate that N well. So I come back here. So what I do is that on this portion I cover this portion with the N well mask. So after that I will expose this wafer to the ultraviolet system. Ultraviolet light is coming. So ultraviolet light will come like this. This is very easy to understand, and this is important to understand that. And once I have decided, once I have deposited the polysilicon on the entire wafer, the light will fall. Okay, this is the UV light coming, all right, light waves. But somewhere here I have deposited the mask, right? So mask means I have two ways of understanding what is mask. Mask is, it is hiding the area behind it, or it is allowing the area behind it for light to pass. Either the light will pass through the mask, that is the function of mask, or mask is also will be there to block that particular area from light to pass through it. Okay, so that depends upon what photoresist we are using. So for instance, we are just saying we are using the positive photoresist, and somewhere here the mask is there because in this area I want N well to be fabricated. So I expose the system to the light rays are coming. So the light rays will pass through the mask in where I have defined it, and other light rays on other areas will be blocked by the photoresist because there is no mask. So once the light rays pass through the mask, on that area the photoresist will get softened. It means it will get melted away. So there is no photoresist now. So I have this structure, you can see now. So once I am done that, I will put this wafer now into the hydrofluoric acid. So I have this hydrofluoric acid, okay, HF, this special acid in which I am using this hydrofluoric acid to etch the oxide. So I'll put the wafer inside. So what it will do is that it will etch the oxide here. You see this oxide is gone in this step. So I am having this diagram now. Once I am done with it, I will just strip off this remaining photoresist. I don't want this now. So I will just take it off, just like you tear off the paper. So once I am done that, I come to this stage. So now what I see is that I have a P-type substrate, and in the area where I don't want N well, that area is covered by the SiO2. This area also is covered by SiO2, but this area is very well exposed. Now I am ready to dig well. So I have two procedures. One is called diffusion, or one is called ion implantation. Okay, so diffusion and ion implantation, these are two different techniques. We are not going to dig details into that because that's the fabrication issues and fabrication methods. So there are different chapters at different lanes, we can talk about that. But just remember, out of these two, mainly nowadays in technology they use the ion implantation. So what they use, that they select the dopant, what kind of dopants you want to fabricate N type semiconductor into the P type semiconductor. Now this is the P substrate, okay, and we want to fabricate N1. So I will use the group 5 dopant, group V semiconductors. It could be arsenic, for example. Okay, arsenic. So I am going to have lot of valence electrons in the outer shell. So what I'll do is that there will be a bombarding of dopants, some gas will be there when the wafer will be put into the furnace, and that ions, those dopants will deep penetrate into the wafer until you know a particular thickness, how much thickness you want. So okay, so once that step is done, we will just remove this oxide from here and from here, and finally we arrive at this anvil. So this is the steps, series of steps we perform using. How many masks we use to fabricate this anvil here? How many masks?
3, 4.
No, only
Sorry.
one mask.
3.
We need only one mask. We used only N well mask because we are fabricating N well.
Okay.
Okay, so they might
So
ask you what
P
is
substrate, can't we take it as mask?
no, P substrate is just a mechanical base or mechanical support, or it's a wafer, silicon wafer, into which we want to fabricate our devices.
Mask means what, sir?
Mask is a layer or a rectangle where we want to fabricate the device, because this is a mask. For example, I say this is the mask of anvil. It means it tells me that I am covering that portion with a special material, okay, and I am allowing the light to pass through it. When the ultraviolet light will pass through it, so it means it will, through this mask, that light will fall onto the photoresist and that will be melted away. It just let's say a layer that specifies where I want to fabricate a particular thing. For example, well or polysilicon or diffusion and all that. Okay.
Okay, sir.
So you see, now we use NWell to fabricate. How many tasks are remaining now? We want to use each of these different masks. So I will use the mask for separate mask for polysilicon. I will use the separate mask for the N diffusion. I will use the separate mask for the P diffusion. I will use the separate mask for contacts, and I will use separate mask for the metals. And this is how this looks like. And mask job is to allow the light pass through it or block the light passing through it. There are two ways depending on what we want and how we want. Okay, so now for a physical design engineer, this layout concept and the fabrication flow is very important. You should be able to know what is mask, what is its purpose, what is photoresist. So when you use EDA tool, for example, to draw the layout of your digital logic, or let's say analog or mix mode. What is mix mode? You will often hear this word, mix mode IP. What is mix mode IP? Mix mode IP is analog, you have digital, analog and digital both in a single chip. Okay, that is called mix mode IP. You can take the notes. So once we are done with this, what are we going to do? We just managed to fabricate NWell. So let's go to next step. What I want to fabricate next? I want to fabricate now polysilicon. So polysilicon, I know what is the mask look like, how the polysilicon mask look like. So I go back to this figure. Can anybody tell me where is the polysilicon mask? Here. This is a polysilicon mask where I have connected two gates of the transistors, right? So what I do there, I know that, look at these lines here. So you can easily distinguish between different masks by their colors and by their diagrams. So what I come back here. So first to start with, I am ready with this final step. I am here. I am done with the N well now. So what I do now, I grow a very thin layer of oxide, gate oxide again. So this is called as silicon dioxide again, or it could be silicon nitride also, depends on what kind of technology is that, what is the application and so on. So you see now this is a very thin layer right over here. And on top of that, what I do is that I want to grow the polysilicon. Okay, because I want to fabricate the transistor gates which are made of polysilicon, and I am going to grow this layer. So what I do is that I use a special technique called as chemical vapor deposition process. So again I go to clean room where the chips are manufactured or chips are fabricated in the plant. That place is called as clean room, okay, or a foundry. And there are different machineries to perform each of the IC fabrication steps. So one of them is called as chemical vapor deposition. So obviously it's a chemical process where through the vapor deposition, this polysilicon layer will be grown over the wafer, okay. And this polysilicon, as I said, is heavily doped.
What is the use of gate oxide?
Which oxide? This thin gate oxide?
It's
This is just to isolate our polysilicon to the remaining portion of the wafer. Isolate the polysilicon from substrate and the L well.
is that gate oxide is an insulator?
Yes, oxide is an insulator, yes.
Okay, sir. The channel between NMOS. So the channel is made up of what, sir? In transistor.
We'll see that. Channel is just a P-type semiconductor. Right over here, you see here. Here is the channel. Here the charge carriers will come based on the applied electric field. Positive or negative charge carriers will come here. And
so let's say these two are in.
And this is the oxide. You see, this is the thin layer. What you see in the first diagram A, you have the final diagram F. So this is the SiO2 or silicon nitride, just the oxide. This is the polygate, and this is the channel is just a semiconductor.
Okay, channel is far below that.
Channel is below the oxide, obviously.
Below the gate oxide.
Yeah.
And is it completely act as an insulator, gate oxide?
Yeah, well, there is some leakage also. The leakage will come right like this from that is called as tunneling effect. Sometimes the charge transport carriers go from this to this also. There is a short circuit, or there is a direct when you deposit charges on top of the gate there, because it's a good conductor, but it's not a perfect conductor. Also the it may be not be it is an insulator, but it may not be a perfect insulator. So obviously there will be some leakage, so in which the charge carriers will try to enter these, will try to cross the oxide, and that's called as tunneling effect, and that is a possibility. But normally this is not the case.
And here gate is completely made up of polysilicon, no, sir?
Yeah.
Okay, sir. Thank you.
Right, so we've seen that we have this N-well, and we grow the thin oxide layer, and top of that polysilicon is grown by a chemical vapor deposition process. And we know that it is heavily doped so that it will act as good as a metal. Why don't we use metal nowadays? In earlier transistors, when let's say 3 decades ago, 4 decades ago, they use metal, but now technology is advanced, so we use polysilicon. So we come to next step. So again, always the next step is that once you grow the layer, so the steps are like this: deposition, then pattern. Pattern means define what you want and where you want with the help of mask, and then etch. These 3 steps will be repeated throughout the IC fabrication process. So what we do is that once we do, we pattern the wafer again. So again, patterning means To pattern it, we first deposit photoresist. I haven't shown it in the figure, but this is how it will be done. Deposition with the photoresist, and then I will come back with the mask. I want to choose the mask. Which mask I am going to choose out of these 6?
N
No,
diffusion.
what I am fabricating now? I am just fabricating gates of the transistors. And what is gate made of?
Poly.
Right. So I am eyeing on this. I am looking at this mask, right? This is how the mask look like. That's why I have grown the layer of it, right? So I will choose the a mask and come back over here, and I will define at this figure. I am looking at figure A, where I want the mask, the polysilicon where I want the polysilicon gates. So that area I will cover with the mask. So what I choose that, I will somewhere here put the mask here and somewhere here. Why I want? Because if I deposit the gates here, look here, I take the laser. This is very crucial to understand and very easy also. So I will choose the poly mask and put it here, and another mask put it here. Why? Because in the P substrate, somewhere here, once I have the poly mask, I am going to have N plus and N plus. So I will fabricate my transistor, right? Why this is interfering with my, okay, this one. And
Sir, you stopped sharing, it seems.
did I stop sharing? Are you sure? Are you
Yes,
looking
sir.
at my screen? Can you look at my screen or not?
Others able to see the screen? Shweta?
No, sir.
No, we are not able to see.
Okay. Wait, maybe that one. Now you can see that?
Yes, sir.
Okay. Fine. Okay, fine. No problem. So we are here. Okay, that got clicked here. So I am okay, so you can see now I have deposited photoresist. Why? Because I have I want to fabricate this gate. So all over I have a polysilicon layer, and top of that I have a photoresist. Then I go for a polysilicon mask. So I know this polysilicon mask looks like this. So in this area I have drawn the squares. That is where I will place my mask, and the light will then come. Okay, these are the masks somewhere here, and then ultraviolet light rays are coming all over the wafer, but only in the area where the mask is defined, the light will pass through that, and because of that the photo mask right over here and right over here will get softened and will get melted, and therefore I will have only these areas where the polysilicon will be there, and rest of these photoresist will then be stripped away. Are you getting my point? And finally this is what I will have the structure. So what I see that the polysilicon gate is standing on top of the oxide. You see here is the thin layer of oxide, here is the thin layer of oxide. So I have managed to fabricate my gates of the transistors, because here I will have N plus, here I will have P plus. I am going to see that. Did you follow my step?
Yes, sir.
Yeah, simple, huh? Then what is next step? I want to grow N plus regions again. N plus regions what? Because I want to define source and drain. Again I will need to define the P plus regions. Why? Because I want to fabricate PMOS transistors, so P plus and P plus. So let's take a look at N plus regions, how we will use that. So where is the mask for the N plus region, N plus diffusion? Which mask is there? Here, you see? How many masks we need?
2.
For the N plus specifically we need 2. This is and this is. And you see their location. One is here. Why this N plus diffusion here?
Yeah.
Because for the PMOS, inside the N well, this is for the N well also, right? We want to have access to N well. So we will use this mask. So again, the procedure is simple. So what we do here is that,
Sir,
Sir, one question, sir.
hmm,
Can you go to that slide where we can see the metal contacts in the N plus diffusion?
this one?
Yeah, in this, correct. In this, there only two regions. I mean, there are only two regions where N plus diffusion is taking place instead of three. Why is it that? Like the middle, the left one that you're seeing is a little bit bigger instead of being in three pieces.
The bigger one is nothing
Correct.
but two NMOS.
Yeah, so they are not diffusing separately. I mean, is it they are diffusing at a time? That's a small confusion that I'm
Yeah.
not able to understand.
Okay. Try to understand this correctly. No, it's very easy. See, this is the mask for N well, and I am showing this. Okay, this is the mask for N well. This is just a symbol. Okay.
Yeah, that is fine. I understood one. N plus diffusion and the P plus diffusion. Those
Okay, so N plus diffusion, I have defined the mask position here. Why? Because you see, this same rectangular I have drawn here. So this is the source and drain regions of the NMOS. In between, I am having the gate of the NMOS. Similarly, for the PMOS, I take a look at N well. Here is that N well, bigger rectangle. Inside the N well, my PMOS is sitting. So PMOS is P diffusion, this blue mask, this one, and just source and drain of PMOS, and here I have another contact, another mask for N diffusion. Why? Because my PMOS is sitting inside the N well and I want to have access to its body. So I have again one more area here for N diffusion.
Okay, so basically, after applying the polysilicon, the N plus diffusion take place over the polysilicon also, but it won't affect the inner ones, right?
Yeah.
Basically,
Right. So you just
Okay.
define one by one all the layers to fabricate your transistors, right?
understood. Sir.
So now we are coming back to this one. Now we are done with this polysilicon gates. So now can we see we have this MOS structure here. You have poly or say metal. This is oxide and beneath is the channel semiconductor. So that's why we have this MOS structure. Okay, next step. What I want to do is that I want to define the active areas. What are those active areas? N plus diffusion and P plus diffusion. I want to fabricate them. I know now where are their positions from this one, from these diagrams, where these positions are. Okay, here is the gate, here is the gate, and just adjacent to gates I am going to have source and drain of each of these transistors. So what I'll do again, 3 steps I'll repeat: deposit, pattern and edge. So what I do is that this is SiO2. All over the wafer I will deposit this SiO2. Then on top of it again I will have a photoresist. Then where I want the N plus diffusions to be fabricated, somewhere in these areas, just next to the gate, right? Because the transistors are there, P plus, sorry, here will be N plus and here will be N plus, right? You see now this area, these diagrams, where I want these transistors to be fabricated. Okay, let me draw it this way. Okay. Yeah. So we have the SiO2 grown here. Look at the figure C. And then we have pattern because we have deposited the photo mask. And then we took the N diffusion mask and we put somewhere here where we want the active areas to be fabricated. And then we allowed the light rays to come, okay, all over the wafer. Light rays pass through the mask where the mask were put, and light rays were blocked on the remaining portion by the photoresist that we had grown. So light rays pass through the mask and the photoresist was exposed and that portion of the photoresist got melted or softened and other photoresist remain intact. So finally we come at the D, and then what we did, we took the wafer in the HF oxide, we put the wafer, the oxide in this region where the mask was there, you see here we wanted the areas, the channels, that got etched, remaining oxide remained there, all over it remained there, only where we wanted N plus diffusion to be fabricated we got the access. Okay, here also it got etched. Why? Because you will have N plus here also, you see we want to have a contact of N plus, so this mask were put here, here and here. Okay, and then photoresist on the top of this, after etching the photoresist on top of this oxide was stripped away. So this is how we come at figure D. Okay, now we are at figure E. What I see is that I use the ion implantation or diffusion process to bombard the atoms, the dopant atoms, to go deep inside the wafer in the areas I have decided to go. So they go deeper, and to a certain thickness I am allowing this fabrication process to happen to a certain thickness. So I am done with having N plus active regions where I wanted them. And finally again, once that is done, I will just strip out this oxide, I will just remove this oxide with some chemical process also. So the final step is like this. So you see now I am done with N well, that was fabricated first, then I am done with oxide polysilicon gates, which is sitting on top of these thin oxide layers. Then I am also done with active N plus regions. So three things I have fabricated. Finally I am going to create the schematic of CMOS transistors, both NMOS and PMOS I want to fabricate. So far any doubt with this? No, right? So we go to next step. Now look at this figure. I want to repeat this process. Can you see now this poly gate is done, active area are done, here also this is done, anvil is also done. What is the new thing you see in this figure A? What is the new thing? New thing is I have defined P plus regions. How have I defined that? How have I defined that? P
Again, same process.
same
like
process,
SIU.
yeah, same process. I will use deposition, then pattern, and then etch. So again I will, for instance, I will just grow the oxide all over, then photoresist all over, then put some mask, P diffusion mask. In the areas I want to fabricate P plus regions, I will allow the ultraviolet rays to pass. They will go through the mask, and the photoresist will melt away. The remaining photoresist will stay like that. Once that happens, I will put the wafer in the hydrofluoric acid. The HF will remove the oxides from the area I defined the mask, and next step I will take off the photoresist from all over. So then I will use the ion implantations, and finally what I do is that I have this P plus here, P plus here, P plus here. Now come at this diagram, what we are doing here. Okay, so field oxide will be grown to insulate the wafer from the metal. Now what I will do is look at the comparison between figure A and figure B. I am putting the field oxide here, 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 here and here also, on top of gate also. Why I am doing that? It is just to isolate each of the regions from each other, okay? So I am growing that oxide with some deposition process to insulate this entire wafer, because I am going to have the metal connections also. I am going to sputter the metal on top of it, and the metal will make the contacts with where I want them, okay? So I will see how things will happen. So field oxide, I will pattern them first with the contact mask, okay? Where I want the contact mask now? Here, because these areas I want to have access to. because this is how I will make the connections. Yes or no? Right? So field oxide will be patterned with the contact marks, and it will leave the contact cuts here where metal will go and will attach, the metal will attach to the diffusions or even to the polysilicon. Okay, even to the polysilicon, like Naren said somewhere, can we connect the poly gates with the metal? Yes, if I put the metal, I will connect the poly also. Okay, so next step, what would I do? I will take the aluminium. Where is the mask for aluminium? You see these blue lines here? Go back. Here is the mask for aluminium. Here is the mask for aluminium. Where it is not present in the area, what is this area? Come up. This is the area where poly gates are there. Poly gates are there. I don't have metal here, but metal is just like this portion, up to this and up to this portion, just covering this one. Okay, so I know how metal mask looks like. I will take the metal mask and I will sputter it all over the wafer. Okay, and then I will again pattern it with the photoresist, ultraviolet rays, same steps, and the metal will just go where I want the contacts, and finally where I don't want them, I will etch them away. Okay, so this is how we are managing to fabricate our transistors in the wafers. So I hope you got the basic fabrication flow. When you as a PD engineer, or when you use some tools, there will be a direct transistor layout cells ready-made available. For instance, you will have this N-well, and in N-well you will have such kind of cell. So that's already connected, so it means this is source and drain, and this transistor is, let's say, sitting in N-well. So this is PMOS. So you will simply pick up this cell from the library, and then for the NMOS you have another, is again the poly, source and drain. This is source, this is drain, this is the NMOS. And this, so you, when you draw the layout, you just take these ready-made transistors and you just define their sizes, length and the width. We are going to see what is length and width, and then make their interconnections. So for instance, you will use this transistor where two gates are connected. So I will draw the extra wire like this. So two gates are connected, something. We'll learn how to do that. Okay, and then source, let's say source is tied to ground. Then for this drain, I will make another rectangle. I will say this is my VDD that is connected, and this is how I will implement any logic function.
Sir, why P plus and N plus are connected in the N-well?
Where?
In N-well through metal.
This one?
Yes.
Yeah, P plus and N wells are connected because you see, when I draw the circuit of an inverter, this is the fabrication of the inverter, right? So I know input, I know output, this is VDD, and this is ground. So what I do now, body, what about the body of each of these transistors? So body is that, I know that the body of NMOS, I show through the symbol like this. This is source, this is drain, this is source, and this is drain. So I know the body of a NMOS is tied to its source. So where is the P substrate? Here, source, drain of NMOS, and that is tied to P. So I have a metal connection here. This is, I will connect them together. What about, yeah, and what about the PMOS? Here, the body of it is tied to source. So N-well is here, this is drain, this is source, and that is how they are connected together. Okay?
Okay, sir.
So now I told you that how we are learning about fabrication. Once I know what is fabrication, I want to learn about layout also. So I just explained you that sometimes you have these transistor cells in the library. You just take them out, you define the length and width. Length is channel length, width is,
Sir, sharing of screen is stopped.
No, sir.
No, sir.
Are you sure? Now?
It is good, sir. Sharing screen is good, sir.
Yeah. Okay. So let's talk about layout design rules. So layout design rules in the sense, I go to library and as I said, I will have the access to ready cells, NMOS and then PMOS again. So these cells are like the gate, for instance, this is source and drain. So these cells are there. So you'll pick up these transistors, whether NMOS or PMOS, and then you will have a schematic screen, the layout diagram screen on your tool, right? Basically, you can ask about your institute whether they are giving access to you for the laboratory, because they informed me there will be another person who will be teaching you laboratory session. So just keep on asking them and just see that when they are going to give you tool access and all that. Okay.
They said after a month they will give
Yeah,
once.
but I think you already know enough theory, so maybe you can just understand whatever the things you have understood. Try to explore the tool itself. I will also then help you to give some tutorial on that, right? Maybe.
Okay, sir. Yeah.
So design rule are in terms of lambda. What is lambda? Lambda is a design rule parameter in the technology library. So when you have, let's say you are designing the circuit or drawing the layout using 180 nanometer technology node or technology process, so lambda is the design parameter which is half of this length, feature size, half of this feature size. This is feature size. Feature size. Okay. So just remember, because when we draw the layout, we don't talk about L and some other parameter. We just remember that we'll talk about the lambda rule, and lambda is half of the feature size, which is the feature size is technology node. So what is the channel length? I have also told you this is basically a distance between source and drain. That is the channel length, and that is nothing but the feature size. So if I have 180 nanometer process, it means it has a minimum polysilicon width of 0.18 micron, and therefore half of that will be a lambda. Now, okay, what is the meaning of this sentence? This is very important. See, I have a P substrate, and then when did I fabricate the source and drain regions initially, or did I fabricate the gate initially?
Gate first.
Good. Gates will always be fabricated before the diffusion, active diffusion regions. Why? Because when you have a gate, I am drawing a cross-sectional view. The top view would be like this. You have this area, active area, and then this is the substrate, okay? And then I am drawing on top view, this is the poly. So when I draw this is the minimum width, and that is nothing but that will define the feature size of the transistor. Or let's say the feature size of the transistor will define the minimum poly width. So when I fabricate the poly width, polysilicon in the P substrate, that essentially sets the channel length without fail, and that also indicates the minimum and the lowest distance between source and drain. Did you understand that?
Yes, sir.
Yeah. So the polysilicon width is nothing but will set what is the distance between source and drain. Okay. So designers always describe this process by means of the feature size. Always they talk about feature size, technology node, 180 nanometer. So you should know this as a physical engineer or VLSI engineer. You should know this one.
So lambda, do we call it as any term?
Lambda is just a design parameter when you will draw the layout. So you will know the feature size or the technology node. So you will not talk about feature size, you will simply say lambda is half of that feature size. So you will always talk about and define your dimensions in lambda, in terms of lambda. When you will draw the rectangles to connect two transistors or several transistors with any layer, metal, poly, then you will always talk in terms about how is the width, how much is the width. You will say 2 lambda is my width, 3 lambda is my width. You will not say feature size multiplied by 3 times the feature size or 4 times the feature size is my width. You will say lambda is 2 times lambda is my width of a particular layer.
Okay, sir. So this lambda is refer only for poly or any other like metal also.
All layers in the given
All layers.
yeah, in the given whatever the set of mask or set of layers, you will have access to lambda is for that. Okay, so lambda rule, they will help the designer to describe the minimum width to avoid the breaks in the line. It means they will tell what is the minimum width. We'll see in terms of diagram now. I will explain you. And they will also, lambda will also tell us when you draw two lines, what should be the minimum spacing between two layers to avoid the short between them. And they will also tell us how much is the minimum overlap to ensure that two layers completely overlap. Right? For instance, I have always been showing you this one. You have this active region, this is P substrate, and then you fabricate the poly. So you see this is the overlap over the substrate here. So that should also be defined. You cannot have arbitrarily very long or arbitrarily too short, right? So these are all set by the design rules. So how much is the overlap and all that. So let us understand in terms
This
of...
width is a constant for all type.
You mean this width?
Yes.
Yeah, this width is constant. This is set by the technology.
Based on the technology, it will change or not.
What?
If
Say
the
again.
technology changes, that width will also change.
Correct,
Or is-
correct, correct. So it means you have like 180 nanometer process. So you will have the width of that poly according to this technology. If you are designing with 10 nanometer, so the poly width will be accordingly that way. Okay.
Okay.
So let's see, now we have a set of design rules for the layout, and this particular technology or library process has two metal layers. How many metal layers we had in the CMOS inverter when we designed it?
One.
Correct. So I am now explaining you a two metal process. I can have three metal process. I can have 6 metal process. It depends on what technology you are using. FinFET, CMOS or bipolar. Okay, there are different types of technology, and each technology having different layers of metals. Even you can have a technology file with two poly process, two poly layers. They call it as a poly 1, poly 2. Sometimes you will hear these words, 2 poly 6 metal process, CMOS process. Are you taking the notes of this? Just remember, just to help you. So see now, I am having an N-well process. Okay, so it means I have a P substrate and I have an N-well process. So already I have an N-well built into that process. So I don't need to specially fabricate a N-well into that process using that technology. Try to understand the meaning of this sentence. When I say I am having a set of design rules for the layouts with the two metal layers in N-well process, it means I am given a process or a technology library where N-well is already defined. So when the chip will go for fabrication, the foundry doesn't need to fabricate, doesn't need to perform those steps that we studied here to specially exclusively fabricate N-well in that process. It's already there. Okay, that's the process is tuned for that particular step. So now let's take a look at this diagram. First rule says, this is just an example rules that an engineer would like to know. Metal and diffusion have minimum width and spacing of 4 lambda. Where do you see I have metal 1 here and I have metal 2 here. I have a diffusion layer here also. So what I see here, there is the minimum width of this metal. This is one layer of metal 1 and this is another layer of metal 1. So the first rule says that the minimum width should be 4 lambda. I cannot have 2 lambda or I cannot have 3 lambda. Minimum it must be 4 because otherwise I will violate the rule. If I am placing during the circuit connection, if I am placing the metal 1 layer like this and metal 2 layer like this, then the spacing between these two should be minimum should be 4 lambda. I cannot have 3 lambda, otherwise I will violate the rule. So these are the simple rules that the designer will have to obey. Okay, now what is if I have a minimum width of metal 1 is a 4 lambda, okay, and I am using a feature size of 10 nanometer, then what is the actual width of this metal 1?
Ten.
20. Feature size is 10 nanometer.
20.
So lambda
20.
is
Okay.
feature size by 2, 5, okay, and I am using the minimum width of this 20 nanometer. What if I draw the metal line of 18 nanometer? I will not pass the DRC, design rule check, okay. This is how it goes. Let's take about diffusion. The minimum width again I have to obey as a designer 4 lambda, and if I have a 2 diffusion layers, say this is n plus, this is n plus, or this is one is p plus or another, whatever it could be, the spacing should be minimum 4 lambda. This is how the rules have to be. So metal 1 and metal 2 layers are shown by different diagrams. You see there are lines here, there are dots here, just to distinguish between the two. Okay, now look about the second rule. For instance,
Sir, will it be there any fraction number like 2.5, 3.5 lambda, something like that, or it's always an integer?
It's always an integer.
Okay.
For a good design practice, yeah. So contacts are 2 by 2 lambda. So this is how these are the contacts, as you can see from this laser pointer. These are the blacks contacts. So that says you see this is the 2 lambda, that is the width and the height 2 by 2, and it must be surrounded by an additional layer over at least 1 lambda. Here I am showing that covering must be 1 lambda. So what is this picture showing? That is showing the contact between metal 1 and the diffusion. So for instance, what is that contact indicating? Let's say I have this P substrate and I have this gate here and I have this active area N plus, this is N plus, and I am having this metal here to make some outside world connection. So I will etch the contacts here, so that diagram is showing this one. Okay, so it is showing that contact will be established there to connect metal to this diffusion. Then this is again metal 1 and polysilicon contact. What if to the gate I have a metal connection here somewhere, so I will have another contact right over here. So this diagram is showing the contact between metal and the polysilicon. These contacts are showing the metal 1 and metal 2, that is called vias. Okay, what is metal 1 and metal 2? How do they connect together? Let's say I have this metal 1 here, this is cross section metal 1, and this is metal 2, let's say M2, and this is M1. Okay, so these two metals will be connected through a special contact, they are called as via. Okay, so that's again the electrical connections. We'll see that what via is when we move forward. So these are the design rules that you will need to obey, and accordingly you will always design your rule. Even if you make a mistake when you run the simulation or DRC, the tool will tell you you came across an error. Then accordingly you go back and you adjust your widths and adjust your lengths and adjust your spacing between the two layers and so on. What about the polysilicon? Look, the polysilicon, there are 2 layers. This is 1 and this is 2. The minimum width is 2 lambda poly. So for the 10 nanometer process, how much is the minimum width I can draw?
N nanometer.
Right? So see now, so this is polysilicon itself is deciding my feature size. So when I draw 2 lambda width of polysilicon, it does mean I am actually not crossing that technology. I am using the minimum resolution that the technology has to offer. If I am designing the layout with the 10 nanometer technology, I am given a polysilicon to draw a minimum width of 10 nanometer, that is 2 lambda. I cannot go below that. So this is the understanding. But generally, as I said, you will have a ready-made cells of NMOS and PMOS in your library that are predefined, that are decided. You just have to pick up those cells and make the interconnection of those transistors to create AND logic, NAND logic, any logic, even mux, decoder, flip-flops, and so on and so forth. Look at the final figure here. Now we are going to see that. So polysilicon overlap, diffusion overlaps the diffusion. Where is the polysilicon is overlapping the diffusion? Can anybody tell me that? Here you see, this is the poly gate. This is again the layout of a CMOS inverter. If you can clearly see that. I have just flipped this. This is, if you see this view over here, this is horizontal way. I just flipped it, I just rotated by the 90 degree. So what I see here, layout in the rotated by the 90 degree. So poly is running over the diffusion areas. Okay. Why there are two contacts here? This width of the transistor, this is the width of the transistor, looks bigger than the width of this transistor. This is the width of a NMOS, but width of the PMOS seems to be double than the width of the NMOS. Why? See, this is the N well in which PMOS is sitting, and this is like source of the PMOS. This is the drain of the PMOS. This is the drain of the NMOS. This is the source of NMOS. Source is connected to the ground, and I know that drain and drain are connected. So this is output Y, and then I have N well, and this is source. This is connected to VDD. Okay, so I have a metal and all this. So dimensions. Now look at the dimensions here. So what are the dimensions? Says that polysilicon overlaps the diffusion. This is the overlap by 2 lambda, where transistor is desired, and has a spacing of 1 lambda where no transistor is desired. So it's just to tell you that you can read these rules and accordingly take a look at these pictures. You see now, when you draw the metal and the definer, the distance between the end of the N well to the diffusion area, minimum 6 lambda. You cannot stretch this layer like this. Okay, so all these rules. Similarly, from N well to another diffusion, again this is 6 lambda. How much is the overlap of gate from the diffusion area? 2 lambda minimum, and so on. Okay.
Why that extra metal contact, sir?
Where? Here, this one?
No, metal contact.
This one, right?
Yeah.
Yeah. So generally, see, the physical region is that we basically have drawn the size of the PMOS. This is PMOS, and this is NMOS. So we have saying that the width of a PMOS, is greater than width of NMOS. Why? Just to have equal conduction through the charge carriers. Why? NMOS operates by electrons. When it is switched on, there is a flow of electrons. And PMOS, when it is switched on, there is a flow of holes, the opposite charge carriers. So mobility of electrons, from physics point of view, mobility of electrons is faster, is higher than the mobility of holes. That is the semiconductor physics. Therefore, to have the equal flow of, to have the equal number of charge carriers, or say same amount of current, usually PMOS dimensions are made bigger than the NMOS. So that's we call as a adjusting the length to width ratio. We are going to see that ahead when we move ahead. So far did you understand these concepts?
Yes, sir.
Okay. Any other questions you have? Let me know. Any general question or question based on this? So now we understood the fabrication flow. Now we understood the CMOS transistor layouts and bit of rules, design rules that the engineers in VLSI industries would need to know how the transistors are fabricated and the layout is carried out. So we'll see in the next session how we are going to draw these layouts for some of the logic functions and how we will use these lambda rules to define that. And you will also come across this why bigger PMOS is having bigger size. So this contacts that I have shown here, these contacts, instead of one contact I have shown two contacts. So if I draw it little bigger, I can have series of contacts here, I can have series of contacts here. That is to have a good connection with the diffusion areas of metal and this one, to have a good contact, because I know that PMOS transistors usually have a lower conductivity than the NMOS. Okay? Any other question?